Hello, my name is Caleb Jepson.
I'm Craig Latta.
I'm Jennifer Overson.
And we are Group 19. Our senior project is a digital microfluidics workstation for the Oregon State Department of Chemistry.
Microfluidics is the precise manipulation of small amounts of fluids with applications ranging from simple solution mixing to DNA synthesis.
Our sponsors, as Caleb said, is the Oregon State Chemistry Department. We'll be working under the guidance of Dr. Vincent Rimshow and Myra Kosajojo. The physics behind our project deals with electrowetting on dielectric. It deals with the surface tension between the fluid and the surface and the fluid and the air. So we deal with Lippmann's equation and Young's equation. We combine them to get this one right here, which deals with this angle theta right here. Theta without an applied voltage. This is the surface tension between the liquid and the gas, the capacitance per unit area of our hydrophobic dielectric surface, and our applied voltage. So basically what this tells us is that if we apply this voltage, we can change this contact angle. So without any voltage, we get this nice smooth bubble. We apply a voltage and it flattens out, creates a smaller contact angle and a larger area in contact with our surface. Okay, before I described how the surface tension and how this droplet wets to our substrate here, how this contact angle is affected by voltage. So now I'm going to explain how we're going to take this droplet based on that theory and move it across a chip. So first off, we're going to have a voltage source and a ground. This is a very basic idea here. This voltage source right here on this electrode, this is like a chip cut in half. So this is our drop, this is our dielectric layer, this is an electrode, and this is our substrate of silicon. So at the moment here, you can see our VCC is connected by a switch to this electrode. This one is high, and it's not connected here, and this one is connected to ground. So we have one high and one low, and this droplet is going to be formed over this electrode here. So as we go to the next one over here, we end up switching these two switches so that this electrode now is high as well. When this electrode is high as well, the surface tension that was here has moved this droplet out to wet it over both electrode surfaces. So both of these electrodes are connected to VCC and the switch to ground is off. So in this third switch over here, we shut off this electrode right here so that this one goes low to ground and this one here gets set to high and stays high, and the droplet has now moved over to our second one. As you saw from my last example, you can see how by manipulating these electrodes, we're able to move a droplet from one side over both to over here. So the final idea behind this project is the lab on a chip design. So we're going over here. Think of this as the top view of our chip. So here we have lots of electrodes, and let's say our chemist wants to pipe out a couple of different chemicals, push a button, and they're going to mix. So the digital microfluidic workstation will move this droplet over to here, move this one over to here, and you can have different protocols. Move them across the board to mix, like they'll combine and then have a mixing pattern. Or you can split them, or you can move them to different areas under different temperature conditions. But basically, through a simple manipulation like this, we're able to program, based on zeros and ones, how to manipulate different drops of fluid on a chip.
Hello again. In this video section, I will discuss three fundamental design requirements in our project. The automation of the manipulation of microfluidics is an exciting one and has many benefits to a chemistry department that is big or small. Currently, a chemist must use an expensive pipette dispensing tool and their time to manipulate small amounts of fluid. When you're paying a chemist $75,000 a year to run tests, this may not be very effective use of your money. Our idea to assist in this issue is a completely autonomous system. This system will be a set and forget type of deal, where a work surface is loaded with chemicals to be mixed, and the user will press a single button to begin chemical mixing and dispensing. When the mixing process is finished, an audiovisual cue will let the user know the machine is complete. Our goal is to make a microfluidics workstation small and cheap enough that it allows you to potentially purchase several of these and have one tech or chemist running 10 to 20 units at a time. Another advantage of automating the manipulation of small volumes of water is an increased accuracy at decreased volumes. Will be able to handle fluids at 500 nanoliters and smaller in a very accurate and precise way. Our second design requirement is the workstation we produce must be simple to use by any user, but very difficult to design something now that will satisfy lab technicians' goals in years to come. To take a proactive approach to this potential problem, we have several solutions we will integrate into the project at this time. For the simple to use portion of the project, we will have a very simple, as mentioned earlier, stop and start button in the front of the case. We will also include a USB hookup that will hook up to any PC so the computer tech or lab tech or anyone can write and download code to the microcontrol chip embedded in the processor. Also, we plan on having a standardized pin pattern for the work surface chips that will be highly documented, and future chips can be built based off these pin patterns.
The final design requirement is that the workstation needs to be appropriate for a lab environment. So this means that it needs to have a safe enclosure that will fit in the lab space. We're designing for about 24 by 24 inches. We will also need to control humidity, which we will do through an integrated fan circuit, and we will include an option to connect to a fume hood for use with certain chemicals. In order to meet our project specifications, we need to be able to supply high voltage to the electrode work surface, and we also need to be able to control that high voltage. The supply of the high voltage is highlighted by this red path, while the control of the high voltage is highlighted by the green path. The voltage exiting the diode bridge rectifier is approximately 170 volts DC. This will be fed into a buck converter, which will bring that voltage down to about 25 volts DC. This will then go to a regulated microcontroller board and a regulated temperature control sensor board. The microcontroller board is going to be used to control the switching of the power MOSFET board via application-specific programming.
The high voltage circuit in our automated microfluidics work platform can clearly be seen through this red path. We will take a 170 volts rectified DC voltage and feed it into a 10x boost converter, where we expect to see nearly 1100 volts DC output. This DC output will be fed into a variable buck converter, which will vary its output between 100 and 1000 volts depending on an input signal from the MCU board. This feature allows us to write programs to handle fluids ranging from alcohol to organic substances and to water. This variable DC output is fed into the power MOSFET board. The power MOSFET board is a critical component in our high voltage management system. This board will take a variable voltage DC from the variable buck converter and control which electrode on our work surface will be turned on or turned off. To make this board work, we integrate a series of driver chips and high voltage switching FETs. The driver chips turn on and off the signal based on the switching signal coming up from the regulated MCU board. And in order to power the driver FETs, we pull voltage from this buck converter to power them.
Okay.
Finally, this DC link to the electrode work surface will consist of as many lines as there are pads on the surface. For example, if we have a surface made of 10 surface pads, we will have 10 lines here. The lines are directly connected to an individual switching MOSFET and the power MOSFET board.
Our timeline is dictated by the academic calendar. On the 5th of December, the project specification is due. The design details include the nitty-gritty details of the individual blocks of the block diagram and design validations, along with a specific parts list. With this completed, we intend to work on the prototype during winter break, and by the end of winter break, we hope to have a completed prototype. During winter term, we're going to work on the completed docking station, and in spring term, we'll be adding additional applications such as mixing multiple solutions and possibly DNA synthesis.